Okay, now that we have a general idea of what a limit is, we want to learn some algebraic ways to find these limits, because looking at the graph every time can be kind of tedious. So this first part of section 2, what you see here is some of our main limiting theorems. So you can see here we have the first one: the limit of any constant number, k, will always have the limit of k. Because it's a horizontal line, it always goes to itself. The limit of x, as x approaches c, is just c. So you can see we're just plugging in the c into x. Then you can see, okay, we've got limit of k times f of x is k times the limit of f of x. So any constant can come out front of the limit. We have the limit of f of x plus g of x is the individual limits f of x plus the individual limit of g of x, and that's adding or subtracting. Similar things can happen for multiplication in property 5. Limit of f times g is limit of f times limit of g. Division works very similar. If you have the limit of a function that's divided, like f of x divided by g of x, that's just the individual limits divided by one another. The one caveat there is, of course, the limit of g of x can't be 0, because if it is, you're having a limit that's divided by 0. We know we can't have that. The limit of f of x to the n is just the limit of f of x to the n, so you can take that power out. And the limit of any root, nth root of f of x, is just the nth root of the limit of f of x. And that's, of course, when n is even, because you have to have a positive limit, because if it's a negative, you can't take the square root of it. Now, basically what all these kind of properties kind of say, it really just says if you have a limit of a polynomial, so I'll just kind of write, this is just kind of a caveat of this. The limit of a polynomial we'll just call it f of x at c is just simply f of c. So if you have a polynomial function, x approaching c of this polynomial, the limit is just f of c. So whatever c is, we'll just plug it in, and that's going to be our limit. So we kind of call this direct substitution. So as long as c is in the domain, we really don't have a problem. When c is not in the domain, that's where we start having issues. But since polynomials have infinite domains, we don't have to worry about that. So we use direct substitution when we're just plugging values in to find their limits. So for example, if I look at this first limit, the limit as x approaches 2 of 2x plus 3, since this is a polynomial, it's just a line, this is simply going to be 2 times 2 plus 3. I'm just plugging 2 in, and that's going to be 7. So this limit is 7. No problem. If I look at the second example, this is the limit as x approaches negative 3 of x squared minus 5. Well, x squared minus 5 is another polynomial, so we can just plug this in as well. So I'm just going to plug in negative 3 squared minus 5. So 3 squared is 9. 9 minus 5 is simply 4, so the limit here is 4. So if we were to graph this and see what happens as it approaches negative 3 from both sides of negative 3, it would get very close to the y value of 4. The limit of sine of theta as theta approaches pi. Now sine has an infinite domain, so really we're just trying to figure out what is the sine value of pi. Well, if we look at our unit circle, the sine value of pi is just simply 0. Remember, sine is the y value on the unit circle, so if you look there, you get 0. Now 4 is an interesting one. This one actually does have a domain problem. If I plug in negative 2 on the bottom, I get a 0 on the bottom, which is bad. But if you look at this, the limit is going to 4, so that's really not a problem. Now if we were going the limit as it approaches negative 2, that would be an issue. But since this is not really a value that's undefined, we can just simply plug it in. So that's 3 over 4 plus 2, that's 3 over 6. So that's going to be 1/2. Example 5 is again a polynomial, 3x squared minus 2. So I could just do direct substitution. So 3, I'm approaching 1/2, so it's 3 times 1/2 squared minus 2. 1/2 squared is 1/4, so this is 3 times 1/4 minus 2. So that's 3/4 minus 2. 2 is 8/4, so that's going to be negative 5/4. So again, when there's no domain problems, limits are really, really easy. We're just basically plugging in the number and seeing what the value is. Now, tangent has lots of problems. It has lots of asymptotes, but if you remember, they're all odd increments of pi over 2. This one's pi over 4, so it's really not a big deal. So this will just be the tangent of 5 pi over 4. Now, the tangent of 5 pi over 4, recall, is the sine of 5 pi over 4 over the cosine of 5 pi over 4. And both of those are just negative radical 2 over 2. So negative 2 radical 2 over 2, negative radical 2 over 2. So this limit is just 1. Okay, let's look at some limits using a piecewise function. Now, if you remember a piecewise function, which we studied a little earlier this year, it's a function that takes different values in different ranges. For example, for this function, it says it takes the value of x plus 3 when x is less than negative 4. So these are all x less than negative 4. So if I did negative 5, negative 6, anywhere to negative infinity, I would use that part of the graph. If I look at this middle part is talking about values between negative 4 and positive 2. But it includes negative 4, but does not include 2. So negative 4 would be included, you use this piece, but 2 you would not. Because 2 is on the last piece, square root of x minus 1, when x is greater than or equal to 2. So that's all values that are going to be greater than or equal to 2. Okay? So different values take different things. Now, limit's not necessarily what happens at the point, what happens as it approaches the point. So we'll look at some left-hand limits, right-hand limits, and whether the limit actually exists at that value. So this first one says, I want the limit of f of x as x approaches 4, negative 4, from the right. So we're looking negative 4 from the right. So if we think about the graph, I don't even really need to know what it looks like. Here at negative 4, I have some part coming this way and some part coming this way. So it could meet, it doesn't have to meet. So I want to know what happens as I come from the right. What happens as I come from the right side? So that means it's going to be numbers that are slightly bigger than negative 4. So that's really going to be this middle part of the graph, because those are values that are slightly bigger than negative 4, all the way to 2. So what I'm going to do is I'm just going to plug in negative 4 for that middle piece. So I'm going to do 2. I'm going to plug in negative 4 for x, so that's 2x squared minus 3. So negative 4 squared is 16. So we have 2 times 16 minus 3. That's 32 minus 3, so that's 29. So the limit from the right is 29. Now the second part says what happens to the limit as it approaches from the left. Well, the left side would be coming from, obviously, just the left side of the graph. Well, the left side of the graph is values that are smaller than negative 4. So in this one, I'm going to use the first piece of the graph. So I'm going to plug the negative 4 into the first piece of the graph. And it's simply just x plus 3, so negative 4 plus 3, which is negative 1. Now you see a big discrepancy between these two numbers. One limit from the right is 29, one from the left is going to be negative 1. So what that tells us, our limit at negative 4 does not exist. Because remember what we learned in the first section, a limit only exists is if the left-hand limit equals the right-hand limit. And 29 does not equal negative 1. So this actually doesn't have a limit. It's going to two different places. So that tells me the graph wouldn't connect at that point. Now, if I look at letter D, it says, what is f of negative 4? That's just plugging in negative 4. So the question is, do I plug in negative 4 to the first part of the second part? Well, I would actually plug it into the second part because it has to be equal to negative 4. And that equality is where I see there. So if I plug it in there, I'm going to plug in negative 4. I'm going to get 29. Which was the same as I got from the limit from the right side of negative 4. So the functional value is 29, the limit from the right is 29, but the limit from the left is -1, so the limit does not exist. Okay, let's look at another one. The next one involves limit of f of x as it approaches 2 from the right, 2 from the left, and then 2. So we're going to be looking at the parts that have the 2. So first of all, let's look at the limit as it approaches from the right. Now again, that's going to be values that are somewhat bigger than 2. So that's going to be kind of values in this region, right? So we're going to be plugging in 2 to square root of x plus 1. So square root of 2 minus 1, well 2 minus 1, the square root of 1 is simply 1. So the limit coming from the right is 1. And again, I picked that because 2 from the right would be values slightly bigger than 2, which is in this region. Now coming from the left of 2, I'm going to be in this top region. I'm going to be in this middle because those are values between -4 and 2. So values that are just to the left of 2, slightly smaller than 2, will be in this region. So I can plug in 2 into that function. So that's going to be 2 times 2 squared minus 3. So that's going to be 4. 4 times 2 is 8. So we have 8 minus 3, which is 5. So the left-hand limit is 5. So again, these limits are different. 1 does not equal 5. So the limit at 2 does not exist. The limit does not exist there. So if I'm looking at f of 2, where would f2 be? It would be in the bottom part, because if you notice, f of 2, it's equal at 2 only in this bottom part. So again, that's going to be the same as the square root, so the f of 2 is simply going to be 1. So the function value is 1. One of the limits is 1, but the whole limit does not exist in this case. Now those are really the two big problems in this piecewise function, because those are the two breaking points at -4 and 2. All the other points are really just plug-in points, no problem. So for example, we have 1 from the right. So if we're going 1 from the right, we're really looking for 1. Now 1 is going to be in this middle part. Now it says right, but this is kind of a continuous part through. So since it's continuous, we'll just plug that into that middle part. So that's going to be 2x squared minus 3. So this one's going to be 2 times 1 squared minus 3. That's 2 minus 3, that's simply -1. And same for all these values that really aren't a problem. -6, I'll just plug it in its appropriate part. So look at -6, that's a value that's smaller than -4, so I'll plug it in this guy, which is x plus 3. So if I go down here, I'm plugging this in x plus 3. So that's simply going to be -6 plus 3, which is -3. So that limit's -3. So if it's not a breaking point in a piecewise function, then you're really just plugging values in. 5 is obviously bigger than 2, so that's going to be this last part here, which is square root x minus 1. So this is going to be the square root of 5 minus 1. Well, 5 minus 1 is 4, so the square root of 4 is 2. So the limit at 5 is 2. So any other value except for those breaking points, we're just plugging them in. So if you look at this last problem, it says, what's f of 10? Well, that's really the same problem because we're just plugging in 10. We just have to figure out which part. And obviously that would be the last part because 10 is way bigger than 2. So we're just plugging it into the square root of x minus 1. So this is the square root of 10 minus 1, which is the square root of 9, which is simply 3. So again, the direct substitution will work with those. Okay, so we saw substituting values in, just plugging the number in to find the limit is really a nice way to go. We saw one case with the piecewise function where you have to kind of figure out which part of the function to plug it in, but still not too bad. There are some ways, though, sometimes when you plug in, you get what's called an indeterminate form. Essentially, when you plug in, you get 0 over 0. Well, 0 over 0 really isn't anything in math that we know what that value is. It actually could be lots of things. So when we're trying to find limits, we've always tried direct substitution first. But if that doesn't work, then we sometimes have to manipulate the expression to make it work. So a couple of ways we'll do this is we'll work on factoring and we'll use synthetic division if you get this 0 over 0. If you don't get 0 over 0, then you're done. You plug in, you get some number, you're really done. Really the 0 on the bottom is the big problem in these kind of issues. Okay? So we'll try to factor and maybe use some division, synthetic or long division, to sometimes help us to find these limits. So for example, here is the first one. This says the limit of x approaching negative 3 of x squared minus 9 over x plus 3. Well, if I plug that in, if I plug in negative 3, I get negative 3 squared minus 9 over negative 3 plus 3. So the bottom is certainly going to be 0 because you get that. So the top is 3 squared, which is 9, minus 9, which is also 0. So we have 0 over 0. So we really don't know what this limit is, so we have to figure out either to factor or use synthetic division to try to find our limit. So when you have the 0 over 0, we're going to try to factor, because this is a pretty easy one to factor. So I'm going to rewrite this as the limit as x approaches negative 3. But I can factor the top as x plus 3, x minus 3. It's the difference of squares. And the bottom is still x plus 3. So really what you see here is these x plus 3's will cancel. So really that original limit is the same as the limit x approaches negative 3 of just whatever's left. And in this case, that's just x minus 3. So I could certainly plug in negative 3 there, no problem. So negative 3 minus 3 is negative 6. So that's going to be my limit. So by factoring, I got rid of that problem that was giving me 0 on the top and bottom. So this limit is just simply negative 6. Let's look at another one. Same idea. You first plug it in. I'll leave you to try it, but if I plug this in, I get 0 over 0 as well. This is the limit of x squared plus x minus 2 over x squared minus 1. 1 squared minus 1 is 0. 1 squared plus 1 minus 2 is 0 as well. So I'm going to try to factor this one as well. So the top, if I factor it, is simply going to be x plus 2, x minus 1. And the bottom is going to be a difference of squares again, x plus 1, x minus 1. So after factoring, you see these x minus 1's will cancel out. So we're just left with limit x approaches 1, x plus 2 over x plus 1, which we can then just plug in 1, 2. So this is just 1 plus 2 over 1 plus 1. So this is going to be 3 over 2. So that's our limit. So factoring is a really nice way to do this. Not the only way. We'll do a division one here in a second. There are lots of other techniques that you can learn at a different time. But for just this introductory section, these are the two big ones we'll use. All right, let's look at 3. Again, if you plug in 4, we have 16 plus 12, which is 28, minus 7 times 4, which is 28, so that's 0. And you get 16 plus 8 times 4, which is 32, which is 48. 48 minus 48 is 0. So this is another one of those 0 over 0 ones. So we're going to try to factor it. Again, this is not a very challenging factoring problem. So we have x and x. Two numbers multiplied to 12 added negative 7 are negative 4 and negative 3. On the bottom, I'm going to factor, so I'm looking for two numbers that multiply to negative 48 but add to 8. That's going to be x plus 12 and x minus 4. And again, you can see what that 4, what makes that 0 on top and bottom is a common factor, which I'll just cross out. So I end up with the limit as x approaches 4, x minus 3 over x plus 12. And now this is very simple. We'll plug in 4. 4 minus 3 over 4 plus 12. That's going to be 1 over 16. So my limit is going to be 1 over 16. So So it's kind of interesting. All these problems, when I plugged it in, I got 0 over 0, but I've gotten very different limits for each one, different values. And that's just because when you cross out that factor that's making it 0, you can get pretty much about anything. Okay, let's look down here at problem 4. We got x cubed minus 7x plus 6 over x minus 2. Again, if I plug in 2, I get 0 on the bottom, 2 minus 2. 2 cubed minus 7 times 2 plus 6 is 0 on the top, because that's 14 minus 14. So we have a 0 over 0, but this is not one we can really factor because we have the x cubed. So in this case, when you really can't factor it, we try another technique. We try to long divide it, or we try synthetic division. Synthetic division is definitely easier, and if we get a remainder that's 0, then it's something we can work with. So I'll go ahead and synthetically divide this out. So I have 1, I have my 0 because there's no x squared, negative 7 and 6. We did a lot of synthetic division earlier in the course, so this really shouldn't be a new technique. But again, the opposite of the bottom, which is 2, and then I just put the coefficients at the top, making sure I put a 0 where the x squared was. Bring down the 1, 2 times 1 is 2, 0 plus 2 is 2. 2 times 2 is 4, negative 7 plus 4 is negative 3. 2 times negative 3 is 6, which is a remainder of 0. So if this was anything that didn't have a remainder of 0, this would be an issue that we'd have to deal with later. But right now, this is no big deal. Got a remainder of 0. So I simply can rewrite this limit as x approaches 2 of x squared plus 2x minus 3. Remember, it's 1 less power, so if we started with a cube, this would start with a square. And now I could just plug 2 in there. So this is just 2 squared plus 2 times 2 minus 3. That's 4 plus 4 minus 3. That's 8 minus 3. So that's 5. So this limit is 5. Now we're not really doing that, but on any of these limits, you could just graph this function. You can see what happens as it gets close to 2. And you will see it would get very close to 5. So we're just algebraically finding what we would know the graph would show. Alright, let's look at the next one. So we have limit as x approaches negative 1 of x cubed plus 1 over x plus 1. Now this one actually does factor, but a lot of people don't know the factorization of x cubed plus 1 because it is a sum of 2 cubes. So we'll go ahead and long divide this one, or do the synthetic division. So we have the negative 1, which is the opposite of this. And on top we'll have a 1 for the x cubed, a 0 for the x squared, a 0 for the x to the first, and then a 1. Now if you know how to factor the sum of cubes, that's fine. And then you could just cancel it. But if not, then you could just use the synthetic division. So I'll bring down the 1. Negative 1 times 1 is negative 1. 0 plus negative 1 is negative 1. Negative 1 times negative 1 is 1. 0 plus 1 is 1. Negative 1 times 1 is negative 1, which leaves us with a remainder of 0. So that's good. So we're going to have this rewritten as the limit as x approaches negative 1 of x squared minus x plus 1. It's really a lot of limits. It's just trying to figure out how to plug numbers in, how to just find the limit by just substituting. But in these cases, you have to do a little more than just plugging in. So now we'll plug in negative 1. So we have negative 1 squared minus negative 1 plus 1. So this is going to be 1 plus 1 plus 1, which is simply 3. And I can take out all the negative signs, so this limit is 3. Alright, so those are just some really easy ways to find limits algebraically without looking at the graph. Please let me know if you have any questions on any of the problems or any of these concepts.